Welcome. Let's start with looking at real numbers or properties of numbers. And these terms are the ones that you'll hear often enough and you should know what they mean. Natural numbers are sometimes called counting numbers. That means it's like counting from when you were a child. You started with one of something, then two, then three, then four. Whole numbers are the exact same thing, except you start with zero first. I don't know who decided to call it a whole different set just because it's a zero, but we are stuck with doing it. Integers are where you have negative numbers also, but this one in red. So it would be like -3 and -2 and -1 and 0 and 1 and 2 and 3 and so on, all the numbers before and after. But notice something about all three of these. All of these are whole, or none of these are fractions or decimals. That's where you get into the rationals. The rational numbers are the ones that can be made as a fraction, like a over b. And that means those are all fractions and decimals that are not like repeating and non-terminating. Irrationals are decimals that continue forever but don't repeat. So let's go and look at a rational number would be like 1/3. And even though that's a decimal that never ends, because it never ends, but it repeats, that means it can be made into a fraction. Any repeating number can be made into a fraction. Or a number like 4/5, which is also 0.8, and it ends there. So those are rational numbers. Rationals you can sort of summarize as fractions and decimals, with the difference that irrationals are decimals that never terminate and never repeat. I'm going to write this so that it's easier to see. Fractions, decimals. Those are rationals. Irrationals, then let's take something like the square root of 2. Square root of 2 is approximately 1.4, and you have to put a whole bunch of numbers after it. It never repeats, and it never ends. And so it's a decimal, but it's irrational because it cannot be made into a fraction. So all of the square roots, unless it's a perfect square, are irrationals. So square root of 16, because it's actually 4/1, is a rational. Square root of 17, square root of 18, square root of 19, square root of 20, 21, 22, 23, square root of 24 are all irrationals because they never end, and they're decimals like that. Square root of 25, that's a perfect 5, therefore it's a rational. These are all real numbers. So they're all real numbers because they actually exist. They're a place on a number line. You can point on a number line and say that's where it is. Of course, with these, you can only approximate, but it is actually an actual number that exists because it's in that form too. Imaginary numbers are different, and we're not going to focus too much on them, but basically they are all, right now at least, they're all the ones where there's a -1 inside the square root, which we have learned is the letter I. So if you have the square root of -17, then that's square root of 17i, because there's square root of -1 times square root of 17. So anytime you have a square root of a negative, that's an imaginary number. So square root of -16 would be 4i. Okay, so there are some options. So imaginary ones are the ones that have square root that don't actually really exist. And that's because you can't take the square root of a negative number. All right, so here are some examples. Let's put some numbers up here. And let's say I'm going to put 17 and -17 and square root of 17, which I've already used. I just like that number. And square root of -17. Okay, and then we'll put the number 0. So let's think about what all of these are as possibilities. So 17 is actually each of these: a natural, a whole, an integer. Sometimes in textbooks they call this one with a Z. I don't care. one way or the other. It's a rational and it's a real. This one, because it's a negative, it's not a natural and it's not a whole number. It's an integer and it's considered a rational and a real. Square root of 17, that's going to be an irrational, but it's also a real. Notice for each one of these are real numbers. Okay, so just because we're focusing on square root or negative or not, you still call them real numbers. And then this is the one where you have to call it imaginary because it doesn't exist. And then 0, we have all of them except for the natural numbers. So it's the whole, the integer, the rationals, and the reals. Okay, so it's in the set of real numbers, they call this. All right, so another one, I'll put that one here. So most of the time it's real, they're all real numbers unless they're this imaginary type because of the negative inside the square root. So focus on the different types of them so that if I were to ask you on an assessment of some type, which these were, you'd be able to check off all of the categories, all of the sets that one belongs to. Now, let's look at properties. Oh, and I did mention here, or I will mention, you can find more about this on page 11. And this next one on the properties, on the top of page 12, we'll find these. And some of these will make some sense. These are good to know for various times that they show up in various parts of math type problems and such. And you'll hear them. So let's quickly review this. Commutative is where the order of them doesn't matter. So you have 8, and then you have x, and then you have x, and then you have 8. So you can do it with addition, or you can do it with multiplication. And you cannot do this with subtraction or division. But in this case, commutative, it's like commuting from home to school and then coming back from school to home. That's another commuting type. That's what the word means in that context too. In the associative property, it's where you associate differently. So in this first one, I'm going to say that 3 plus 4 must be done first, which in order, going in order, we would do that. But in this case, I'm going to say with parentheses here that you have to do 4 plus 7 first. It does not affect this problem because it's adding, all adding, or if it's all multiplying, it would be also the same property. So I could do like 3 times 4 times 7 and put these in parentheses. And that would be the same as 3 times 4 times 7, as long as they're all multiplying and they're all adding. Cannot do this again with subtraction or division because it wouldn't work. The order changes, or the negatives change it, or the dividing changes it. And an identity problem, if you are adding, all identity means is keeping it the same. Keeping it the same. So when we add, that means if we have the number 5, we add 0 and we get the same. If we're multiplying, we would multiply by 1 and we would get the same. So these are the things that you do for an identity problem. You either are adding 0 to keep it the same, or you're multiplying by 1 to keep it the same. This one's called the addition, the identity property of addition, and this one's the identity property of multiplication. Now, for an inverse, this is when we are going to either add, let me try to do this. So, add to get 0, or multiply to get 1. So that means if I have the number 23, I have to add a negative 23 in order to get 0. So this would be considered the inverse of it. So if I have a 23, I would have to multiply by 1 over 23 to get the number 1. So this would be the inverse. So that's considered the inverse, and the other one's considered the inverse. For the distributive property, this is something that you have used a lot, so it's actually something I would say you're probably very familiar with. Okay, let's take a look with the distributive property. 7x plus 5. You're used to multiplying this to get 7x plus 35. When you take out a common factor, like we have 7x plus 35, and we divide them both by 7 and put 7 in front, that is actually, even though it's taking out a common factor, that is actually also considered the distributive property. It's just going the opposite way. Right? Okay, now let's take a look at, give a couple of little samples here. All right, and I meant to do that with the others. Let's do a couple of different ones. Let's do number -6. So negative, so it can't be a natural number, and it can't be a whole number. So that means it's an integer, and it's irrational because it can be -6/1, or it is automatically. It's not irrational because it's not one of those fractions that ends, or that doesn't end and doesn't, decimals that do not end and do not terminate. Whoops, that means the same thing, that do not end and do not repeat. You have to really stop thinking about it. It's an actual real number, and it's not an imaginary number. So that means it would be these others here, these integer, rational numbers, and real numbers. Okay, now let's try this one where it's square root of 12. So the square root of 12, well, there's actually a perfect square in there because that's the square root of 4 times 3. And that means this is 2 squared, so we can take that out. That's actually 2 root 3. Because of the root 3 part, that means that it's one of those decimals that never ends and never terminates. So we know that that's an irrational. That means it's not this, not this, not this, and not this. And of course, it is a real number, and it's not imaginary because it's not a negative square root. That means it's these two here. Okay. Now on this next one, let's do a property illustrated by, let's think of one up here. And so I'm going to do 53 times 1 over 53. Okay, so what happens when we do that, you multiply it and you get the number 1. So when you're doing that to get the number 1, you're doing the inverse property. Okay, now let's take a different one. Oh, and actually before I go on that one, let's say it was for the addition one, it was 53 plus a negative 53, or negative 53 plus 53, we'd be getting 0, and that's the addition property, or inverse property of addition. So both of these would be inverse properties. That's separate from the identity property where you keep it the same. So for the first one, we'd be multiplying by 1. The second one would be adding 0, and then we'd be keeping it the same. So these two, you have to be careful not to get it mixed up. All right, so let's think of 34 times 12 equals 12 times 34. All I did is reverse them, but with multiplication, we can afford to do that. So that means we're going 34 times 12, and then it could be seen as 34 times 12 that way, but it's going the other way. That makes it the commutative property. Right? And so these two, the associative property, look over that one as well to make sure you're comfortable with that. The distributive property, if I were to do this, where I did, let's say, well, actually, let's do that. It's 3x plus 12 is equal to 3x plus 4. It looks like I'm taking a common factor out, but in doing so, that makes it distributive property because it's just simply the opposite of multiplying it in. All right, that's enough for practice. Those who are remembering or thinking about the differences of those. Make sure you're comfortable with understanding what those words mean, please. Thank you for listening. I hope this helps.